am Miriam Rateike.
And I am Ayan Majumdar.
And we are presenting our paper, Don't Throw It Away, the utility of unlabeled data for fair decision making. This is a joint work with Olga, Mineeva, Krishna, Gummadi, and Isabel, Valera. Why do we think about fairness when algorithms take decisions? Typically, a decision-making algorithm is designed to be as accurate as possible. However, in societal settings, we also want to assure that algorithmic decisions are aligned with societal values. Let's think about a university admission example. First, individuals apply at a university. These are our applicants. The university decides whether to accept or reject the applicants. Then, for accepted applicants, the university observes their performance, for example, the university grades. But for rejected applicants, the university will never know how they would have performed. Let's say the university would like to automate this decision process. They give us data from their past decisions from the previous years and ask us to develop an algorithm to take the admission decisions. They also tell us that the goal of the university is to accept highly talented students and that often talented students had good university grades. Now, how does this look like? Let's take another look at how the data that the university gives us is generated. The university aims to find people with high talent, indicated by Y and called the ground truth target of our decision. When a student applies, the university does not observe the talent. It observes the individual's sensitive attributes S, for example, gender, and their non-sensitive attributes X, for example, high school grades. High school grades are generated by the hidden talent and are an indicator of it. However, high school grades are also influenced by gender. That means features X that we observe are biased. The university takes a decision based on X and S. Once a student is accepted, the university would like to know if their decision was a good one. Ideally, they would like to measure talent. However, talent is not directly measurable. So instead, the university measures university grades, which we denote as Y tilde. University grades are influenced by talent and therefore an indicator of it. This is also called the proxy label. While talent is not influenced by gender, university grades are, in contrast, influenced by the sensitive attribute S. Y tilde is therefore a biased proxy label of our ground truth target. Now, in this scenario, there are two kinds of biases that could exist in our data. First, label bias. This is when the observed labels are biased. Here, we have seen that the university grades are our proxy label and influenced by gender and therefore biased. The second type of bias we find here is selection bias. This bias occurs when the policy that took the decision in the past did not decide at random. In this case, our labeled dataset is not independent and identically distributed. That is, it is not an IID sample of our population of interest. If, for example, in the past, the university only accepted students from one gender identity, the labeled data only contains those students, and we have no labeled information about other identities. Classification approaches use a deterministic policy that decides according to a threshold. For example, an individual gets accepted, meaning decision D equals 1, if its probability of having a high grade is greater or equal than a certain threshold. It has been shown that if labeled data is not an IID sample, threshold policies training on labeled data become suboptimal and unfair. We therefore need a different approach that goes beyond standard classification.
Previous work approached the problem not as fair classification, but instead as fair decision learning. Now, what does this mean? Well, to tackle the biased proxy labels, the prior work suggests to incorporate a fairness constraint in the learning process. Further, to tackle selection bias, they learn a stochastic policy where, instead of thresholding, the decision is sampled from an individual's probability of having a high grade. The policy is also learned online, so it gets updated over time as we see more data. Training a stochastic policy online allows for exploration. So at times, we accept individuals for whom we previously had little information about. To further correct for selection bias, we need to apply bias correction as well. Together, this learning process has been shown to be optimal and fair. We refer to this learning procedure as fair log, and this acts as our baseline. Unfortunately, there are certain practical problems that arise from the fair log learning procedure. Firstly, while tackling label bias, fair log proposes to use fairness constraints in the loss function. However, this explicitly trades off the utility for fairness. This means that we need to accept a lower amount of utility if we want to be fair. Secondly, fair log tackles selection bias using exploration and bias correction. But this leads to a high amount of variance in the learning process. That is, across time, different fair log policies yield very different values of utility and fairness. This variance makes the learning process unstable. So our question is, can we perform better? What we observed is that the prior approach only uses labeled data. However, in practice, such as the university application process, we often reject many more applicants than we accept. These are all the students for whom we observe their features, but never see how they would have performed in the university. So we throw away a potentially large fraction of the data.
We asked ourselves, can we use the labeled data to get rid of the fairness accuracy trade-off and allow for a more stable learning procedure? We proposed a new policy framework called Fair All that uses both labeled and unlabeled data. Now, what do? Instead of using fairness constraints like the previous approach, we first learn a fair representation Z of the observed features X and S. Here, we rely on a conditional variational autoencoder. Then we learn a stochastic policy, like in the previous approach, but here we take decisions based on Z instead of X and S. Then we follow the previous approach in using online learning and bias correction. How does our approach perform? Tackling label bias with fair representation learning allows us to get rid of the fairness utility trade-off. Importantly, this is only the case when the ground truth target Y is unbiased, meaning independent of S. Let's take a closer look why this is the case. Remember, this is the generative model of our data. We see that the ground truth target of our decision Y, here the talent, is unbiased, meaning not influenced by a sensitive attribute. However, the observed proxy label Y tilde, here the university grades, is biased. If we take a decision according to Y, where Y is independent of S, the decision is not influenced by the sensitive attribute. Deciding according to Y is demographic parity fair. That is, we accept the same proportion of individuals for different gender identities than present in the population. Additionally, we are counterfactually fair. This is a causal notion. At a high level, a decision is counterfactually fair if an individual, had it been with a different gender identity in a counterfactual world, it would have received the same decision as in the factual world. With fair all, we approximate Y with a latent variable Z. Importantly, we do so in a way that Z is independent of S. Here is how unlabeled data helps us in that. We see that X contains information on Y. When we use the potentially large amount of unlabeled data alongside the labeled data, We are able to learn a representation Z that better approximates Y than if we only rely on labeled data. We then learn a policy that decides according to Z. We empirically show in our paper that our policy, in contrast to the previous work, is indeed demographic parity and counterfactually fair. This is how we tackle label bias. Now, how do we tackle selection bias?
For tackling selection bias, we follow a similar approach to the prior work. That is, we also utilize exploration along with bias correction. However, we show how we can use unlabeled data to learn exploring policies in a stable way. While tackling selection bias, the prior work used only labeled data. So they applied bias correction on the entirety of the loss function, and this led to a higher amount of variance. Fair all, on the other hand, uses both labeled and unlabeled data. This reduces the need for bias correction to only a part of our loss function, and this reduction leads to lowering of the variance. So for fair all, we showed how using unlabeled data can lead to a more stable policy learning process. We will now show some of our empirical results. We first use synthetic data to see if fair all can actually approximate the ground truth policy. That is, the policy that decides based on the hidden ground truth target. We plot the utility, the demographic parity, and the counterfactual unfairness across 200 learning steps. In terms of utility, where higher is better, both fair all and fair log asymptotically reach the utility of the optimal policy, shown by the black line. However, in terms of unfairness, where lower is better, we see that fair log fails to reach the optimal fairness level. In comparison, fair all reaches close to zero unfairness, which is the optimal fairness level. And this is true for both the notions of demographic parity unfairness as well as counterfactual unfairness. Next, using real-world data, we explore if fair all is an effective learning process. That is, we measure how much utility and fairness is accumulated during the 200 training steps. We use the real-world compass dataset, and we compare fair all to the prior work, first without the fairness constraint, which is unfair log, second with the fairness constraint, which is fair log. Comparing unfair log to fair log, we clearly see that adding a fairness constraint helps to accumulate less unfairness. However, it also reduces the amount of utility we gather. In comparison, fair all not only accumulates lower amount of unfairness than fair log, but it can also gather more utility than unfair log. So we see no trade-off between utility and fairness that is accumulated during the training process. Finally, we compare the stability of our policy learning process to fair log. We measure stability using the metric temporal variance for fairness and utility. That is, we measure how much fairness and utility vary with respect to the mean metric value mu. We measured this over the last 125 time steps. So after we give all the methods some time to learn. Note that we measured the variance for a fixed unseen test dataset. Using compass data again, we see that fair all achieves lower temporal variance for both fairness and utility, while achieving better values for mu as well. What this means is that fair all is able to provide a more stable learning process across time. So to conclude, in this work, we developed a novel fair online decision learning approach. In this approach, we utilized both labeled and unlabeled data to capture the hidden ground truth information. We showed how we can perform latent variable representation estimation in an online semi-labeled setup. And finally, we empirically verified the optimality, effectiveness, and stability of our policy learning framework. Thank you very much for your attention. Please check out our paper for more details. We are looking forward to discussing our work with you in person at Seoul, or feel free to approach us online.